In this segment, I want us to start making some definitions using the template for primitive recursion. Let's start off with a function that gives us the power of 2. So for example, power of 3 is 2 to the power of 3. Power of 5 is 2 to the power of 5. So here I've started the template. We have to say what power of 0 is. We have to say how to get power of n from power of n minus 1. Well, any number to the power of 0 is 1. So that gives us our starting point. Now, what about how do we go from 2 to the power of n minus 1 to 2 to the power of n? Remember, 2 to the power of n is 2 times itself n times. So what we need to do is multiply by 1 more 2. So here we see that power of n is 2 times power of n minus 1. And we need to give some value if we ask for a negative power, and I'm simply going to say 0. I leave it to you to try some examples of calculation using this definition. What I'm going to do now is just show you it in action inside the Haskell interpreter. Here you can see that I've included the definition of power, and so I can say what is power of 0? The answer is 1. What is power of 1? The answer is 2. Power of 2 is 4, and power of 3 is 8, and so on. And if I ask for power of minus 2, I get the answer 0. So it gives an answer for every integer, and it's giving us the correct power when the integer is positive, when it makes sense to use that. Okay, let's go back to the presentation. We've seen power in action. Let's look at another example. Let's look at this. It's a function, slightly different function, and when you look at the type, there's something different going on there. You can see SumFun has 2 arguments, but the first of those is itself a function. And I've shown you a formula for SumFun just below. What SumFun does with a function f and a number n is it adds up the values of f at 0 and 1 and 2 all the way up to n. So if we had a function id, the identity function, then SumFun of id n is just the sum of the numbers from 0, 1, 2 up to n, because id of 0 is 0, id of 1 is 1, and so on. So that's what, so SumFun is the result of adding all the values of the function from f of 0 to f of n. How does that work in the template? Well, the value at 0, there's only one value to be added. That's f of 0. So what we have to think of, the crucial case always, is how you get from the n minus 1 to the n value of the function. And if you think, what do we do? SumFun f of n is the value of all those, the sum of all those values of f right the way up to f of n. So what we need to do here to get from SumFun f at n minus 1 to SumFun f at n is to add the value at f of n. And that's precisely what I'm writing here. And then again, we'll complete the otherwise case with a 0. So just reading this again, it says SumFun is giving us the sum of f of 0, f of 1, all the way up to f of n. So the first case, when n is 0, the answer is f of 0. When n is bigger than 0, it's sum of all those function values of f applied to all the way up to n minus 1, plus f applied at n. Let's drop back into GHCI and see this in action. So here's SumFun. Let's add up some powers. And why not? We can see what power 0, 1, 2 and 3 are. So let's do the SumFun of power up to 3. And you can see that indeed is 15. It's 1 plus 2 plus 4 plus 8. And similarly, if we do some fun of ID up to 3, we should get 0 plus 1 plus 2 plus 3, which should be 6. And indeed, that's what we get. So you can see that, that function in action. So we've seen some fun at work inside the interpreter. Let's finish with, I think, a really nice example of primitive recursion, because it's not obvious that there is a formula for this. So the question I have is, I give you a piece of paper. What's the maximum number of pieces you can cut it into, making n cuts? So with no cuts, you have one piece of paper. With one, you have two pieces of paper. But what is the general case? And the way we work out the general answer is to look at this example here. You can see the black lines are the number of pieces we've got by using 3 cuts. And the red line shows what we can get additionally with 4. And you can see what we have done. We have created 4 new areas by making that red cut. It's cut the 3 existing lines, and in cutting those 3, it has created 4 new spaces. So this shows us that in the case of n, if we go from n minus 1 to n, we add n new pieces. Now remember, we're talking about the maximum, where it's not the minimum. If all the lines were together, we just create 2 cuts. So we're talking about the maximum. And what we're saying here is that when we go from n minus 1 cuts to n, we get n more pieces. And that's enough for us to make a definition. And here's our definition. It says, if we have 0 cuts, there's 1 piece. If we have a number n bigger than 0, the number of pieces you get for n is the number of pieces we got for n minus 1 plus n more. And so there we've used primitive recursion to solve this, where the formula itself was not obvious. So that concludes this segment, where I've shown you 3 different examples of using primitive recursion to define functions over the natural numbers. And I'd like you to try using those in practice, also to try doing calculations using those definitions, particularly perhaps this last example. And you can try out see if you can manage to cut a piece of paper into those number of pieces using, and you've got your target from this function defined here. So we'll also be going over other examples of primitive recursion, and I'll be expecting you to do that for yourselves.